Okay, so looking at two things here, the area of a sector first of all, and then followed by how to go and calculate the area of a segment. All right, so a sector is defined as the area encompassed by two radii, which we've kind of got here and here, and an arc. So here's the arc, and so that's really the area of a sector that we've got there. And it's a very simple formula, and the area of a sector is just this. Area is equal to a half r squared theta. Okay, so very straightforward, but theta must be in radians. So theta is in radians. And there's our equation there. We'll put that in a nice little box so that it's an equation that we remember. Quite a simple one. So let's just go ahead and apply that. So here I've got a sector with an angle of pi over 6 and a radius of 9 millimeters. And again, you'll probably be told that this is a sector that forms part of a circle. I haven't drawn the circle in there. You don't need to do that every time, but we do this. So write out the formula, a half r squared theta, and then some substitution, a half times 9 squared times pi over 6. And you just put that on the calculator. Now notice that because there's no sine or cosine or tangent there, it doesn't matter what your calculator is set to. So even though the answer is in radians, the calculator doesn't have to be set to radians. And so if we work all that out, it comes to 21.2, and because we're working in millimeters, the unit is millimeters squared. So really straightforward to use. It's just a matter of knowing that formula and then applying it. Well, let's have a look at the proof for this. So why does that formula work? Well, the area of a circle we know is pi r squared, so this is circle area. And because a sector is just a part of a circle, so if you've got a circle there, and here's my sector, you can see that forms a part of that circle. And that part is defined by that angle there. And so the area of a sector, we can define it like this. Therefore, that's that angle. Now, in radians, the 360 degrees, or the full turn, is 2 pi. So that theta over 2 pi gives me the fraction of the circle of which area I'm calculating. So then it just becomes times pi r squared. Okay, so there's the fraction of the circle times the area of that circle. Notice that pi cancels out, and therefore I'm left with a half r squared theta when we're just rearranging, which is what we give as the formula. You don't have to know the proof, but you do have to know that equation there, which is just a half r squared theta. But it's nice to know where that kind of stuff comes from. So that is, very quickly and easily, the area of a sector. Now, segment's a little bit different in that it doesn't go through the middle, but it does pass through, or it is formed by an arc. So basically, it's a line that goes from the 2 points of an arc straight across. And that's the segment that we've got there. So let's go and look to see how we can calculate all of that. And I'll give you the equation first of all. The area is equal to a half r squared theta minus a half r squared sine theta. So that's the equation for it. It looks incredibly long, but when I explain it to you, you'll actually see that it's not too bad and it's relatively easy to remember. Sometimes you'll see it written like this. It's a half r squared and then brackets theta minus sine theta. And you can probably see the reason for that is that we've just taken a factor of a half r squared theta out. So there they are. It's the same same equation for both of them. And for both of them, theta is in radians. So it must be in radians for that to work. Right, well, let's have a look then and see how does that work. Where's the proof of this? Well, the proof is in this, is that I'm going to draw sort of 3 circles here. And in one, I've got a sector. In the second, I've got a triangle. And in the third, I've got a segment. And what I want you to see is that if I start with the area of a sector, subtract from that the area of a triangle, I'm left with the area of the segment. And that's where that comes from. So we'll color it in to make it look nice. So a bit of orange, a bit of green, I think. That looks nice. And then everyone knows that leaves you with pink. So look, there it is there. So hopefully you can see, you know, there's that bit that's left there, isn't it? Okay, there's your, so if you start with a sector, take the triangle off, and what we're left with is that is the segment. Okay, so basically it's sector minus triangle is equal to segment. Now the area of a sector we just dealt with, and that's a half r squared theta. And the triangle, well, we know that from previous lessons, is a half r squared sine theta. And therefore that combines now into half r squared theta minus sine theta when we take a factor of that out. So that's it there. It's a longer equation to use, but if you remember those two things, if you know the area of a sector, if you know the area of a triangle, and then we've got the area of a segment. So let's do an example. So we'll get a nice circle here, and let's say that we've got a circle with a radius of 10 centimeters, an angle in the middle of 5 pi over 6, and I'm after the segment here. So to calculate the segment, you do need, okay, so you do need, again, the radius, and you need an angle. And so if that's not supplied, then you're kind of stuck. You could work it out if you had the arc length. There are ways of doing that, but basically what we need is we need that angle at the middle, and we need the radius of the circle to be able to work this out. Right, we write that out. So area is equal to a half r squared theta minus sine theta. This is a little bit easier on the calculator to work out. We just substitute. So it's a half times 10 squared times 5 pi over 6 minus the sine of 5 pi over 6. Make sure that your calculator is set to radians, and if you do that, you'll get 105.9, and I think we set the unit in centimeters, and we've got centimeters squared.